Hello and welcome back to the Oxford Online Maths Club. My name's James and this week I'm joined again by Beth.
Hi guys.
Beth's on a slightly spotty Wi-Fi connection with at least a tiny bit of lag,
Sorry.
but that just puts Beth on a kind of equal footing with chat. If you want to join in with chat, there's a live chat underneath. At the moment, it's just me saying what we're doing in live chat. That is at slido.com/OOMC, or go to slido.com and put in the event code OOMC for Oxford Online Maths Club. And if you go over there, then you will find that you can say hi, like these people are saying. There's Joseph and Aaron in chat. You might like to say hi to Beth, who you will recognise from, what was your episode, Beth?
Fundamental theorems of calculus.
Fundamental theorems from the start of this season of Maths Club. And you might recognise Rowan, who is helping in chat. Rowan was here last week, approving chat and making sure that nobody swears or divides by 0. Hello to Rhea and Felicity and Joe and Anonymous. You can be anonymous in Slido chat. That's one of the reasons we use it. It's one of the good features, right? Anonymous, ability to be anonymous. Sorry, I'm looking at Beth. You can't tell I'm looking at you, Beth, because whenever I think of anonymous chat, I think some of them eventually turn out to be not anonymous in the end. Right.
Am I blurry?
No, I just mean, oh, there goes Beth. So adverts quickly while I get Beth back. Mentioned it last week, but I'm going to mention it again. There's a summer school hosted at Murray Edwards in Cambridge that you might be interested in if you're female or non-binary and hoping to do maths at. They say maths at Cambridge. I think maths at Oxford as well. I didn't want to say that in front of Eve, but I think Eve's summer school might be good for Oxford applicants as well. We've got quite a lot of past episodes, including previous episode with Beth that you can get on the Maths Club homepage. I'm going to zoom in a bit. Maths Club homepage over here. If you somehow find us on YouTube without finding the Maths Club page, hey, this is where we post our previous episodes and a bit of further reading. So if you want to read more about graphs from last week, there is a website where you can read more about that. Click on further reading. Hi to George and Murray and Hamish and Lucas in chat. I just want to say, before we get going, let's do the how was your day poll. And Beth, maybe you can tell me how your day was on a scale of 1 to 5.
Can you hear me still?
I can actually, yes.
Oh, amazing. Okay. My day. Well, I actually just did a tour around New College for prospective students, so that was fun.
Very nice.
And it's also very warm in Oxford and like really sunny and nice, so I've had a good day.
I'm actually really struggling, and that's sort of feeble because it's only about 16 degrees, but that's really like, oh my goodness. Not sure I can handle all of this. Somebody voted 1 star for their day, just really quickly, and I'm always looking out for people who vote 1 star or 2 stars. You're having a terrible day and you've logged into Maths Club. Let's hope that maths is the answer. That summer school that we put on screen just now was mostly STEP. It uses STEP because it's explicitly in Cambridge for people interested in Cambridge's admissions test. They use STEP questions over there. Just want to put Eve's maths on screen again. I didn't want to say too much in front of Eve last week because I didn't want to embarrass chat, but I think chat did really well with Eve's live stream last week. Beth, they had this like hypothesis, this idea about this kind of game theory thing on a graph. These two characters are chasing each other around the graph, and there's kind of complicated sort of game theory part to it. And we had a hypothesis, and that wasn't quite correct. And then chat was refining the hypothesis. It was really, really good stuff. We'll gas up chat before we get going. Right, chat is mostly having a good day. They're at
Well done, chat.
Well done, chat. Yes, chat's mostly having a good day. Hello to Jammy Dodger. Every week a different biscuit. Although weren't you Jammy Dodgers last week as well? I've worked out that there's a lot of biscuit theming in chat this year, and it's maybe all the same person, different biscuit every week. Which is, I guess, a variety from Formula One drivers and mathematicians, which is what we've had in previous seasons. True. Right, okay, chat. Good to have you with us. Glad that you're having an okay day, unless you're not. I've got a problem for you that I'd like you to think about. Maybe you've seen it before. It's a kind of logic puzzle, maths puzzle. Here's the scenario. You're out camping, and one morning you step out of your tent and you see a bear. And because it's an art stream, I'm now required to draw a bear. You run.
I'm looking forward to this.
Yeah. You run 1 mile. It's got a head, right, and little ears. Rawr. Rawr. It's angry. You run 1 mile south, then 1 mile east, then 1 mile north, and surprisingly, you find yourself back at your tent. And the question is, what colour was the bear? Well, now I've drawn it, I guess people can look at the bear, but let me make it like a mysterious colour, question mark coloured. It kind of looks a bit like a cross sheep, doesn't it? Let's get like a little tummy. Okay, little tummy. And there's more sheep-like, if anything. Right, okay, I'm going to look up how to make bears look like bears. Beth, have you seen this puzzle before?
I have. This is such a classic.
Yeah. Okay, 3 people in chat have, I think, seen this puzzle before. If you haven't, then the kind of meta puzzle skill is perhaps, how would you possibly know the colour of the bear? What's a surprising colour for a bear? Oh wait, now that I think about it, a meta skill might be, what's the title of the live stream? I've got an episode. I've put the episode title in, haven't I? That's kind of given it away. Okay, so welcome to this spherical geometry episode. Do you want to describe? Let's ask Beth. Beth, do you want to describe what's going on with the bear and the tent?
Oh, you might be catching me out on my bear knowledge. So the idea is that you're at the North Pole. So if you run south and then east and then north again, you're just back at the North Pole, and that's where the polar bears are. So the bear is white.
Nice. So you run south away from the North Pole, you run east, but that takes you around on those lines of latitudes that we had at one point a few weeks ago. And then you run north again and you're back at the North Pole. Fantastic. Good. Okay, people in chat coming up with variants, but possibly seen it before. Possibly very nice. So the thing I like about this is that you get information about the bear because you must be at the North Pole, which is where you get polar bears. And you also get information about the tent. The tent has to be at the North Pole. Is that true? I don't know. So I think I've seen this puzzle before, and the first time I saw this puzzle, it went a bit like this. Somebody told me the puzzle, and then I had to think quite a lot, and then I came up maybe they told me about the North Pole thing. You're at the North Pole, you go south, you go east, and then you go up again. Since then, I've thought about it a bit more, and there's a second solution. Yeah. I don't know if you've seen this bit before, Beth, but there's another solution.
I don't think I have, no.
Yeah, so it's really weird. Hamish has put it in chat, so credit to Hamish as well. But this other possibility is, so I'm going to try and draw this with like the South Pole, where the route is something like you're a bit north of the South Pole, a bit more than a mile. You run south, and then you run east, and that gets you all the way around the South Pole on quite a small circle. And then you run north again, and you end up back at the point where you were. So you sort of go down all the way around the South Pole. You do a little lap by running exactly 1 mile east, and then back up again. And maybe your tent is down here. That's the tent. So then it's a geography question. You have to know that there are no bears down there. You only get bears at the North Pole, not at the South Pole. Which adds a layer of geometry to it. Yeah. Okay. So I think I've seen this puzzle before with just being told it's at the North Pole. I like the fact that there's like a sneaky second solution at the South Pole, but then the puzzle still works because there's no bears down there. Right. Anonymous would like to start running with the bear. I suppose it doesn't say in the puzzle what happens to you when you get back to the tent. It's not obvious if the bear has followed you around this triangle or if the bear is sort of still waiting for you Maybe the bear understands spherical geometry and will just wait for you down there. Yeah, so, okay. Question in chat, which we should discuss. Are you running in a straight line? So Anonymous says, does this mean you're not running in a straight line? Question mark. But we could also say, are you running in a straight line? What do you think? We could sort of argue that both ways, couldn't we? I'm going to put Beth on the spot because you're here. chatter on the spot as well, but it's easier for them to hide. Hi Beth. What do you think? Does that count as a straight line? So I think maybe they're worried about this one where I run around the sample. I don't know.
Well, what would you say is a straight line?
Yeah, good question. Definitions, like it.
I think.
I've replaced my question with a different question, which is, what's a straight line? And for that, I think I need something that works in like flat space that you've met before, and also something that works on the surface of a sphere. Because I want to talk about spheres because we live on a sphere, more or less. Oh God, is that going to get comments on YouTube? I don't know. I'm a bit scared of YouTube sometimes.
That is true.
I put in more or less because it's an oblate spheroid, but also because maybe it's flat. Maybe they'll help me get away with it. Why has Mario put an arrow there? Mario's had a mild redesign, which is slightly freaking me out. So for me, a straight line is so for me, a line segment is, let's put A at the front. Line segment is the shortest distance between 2 points. Let's go shortest path between 2 points, and then the length of that line segment could be the distance. So this works quite nicely in Euclidean geometry, which is the sort that you learn at school or equivalent. We should have some sort of straight line that goes straight from A to B. So then the question, I suppose, if we're on the surface of a sphere, can we make sense of that definition? Maybe the answer is no, there's no such thing, right? Because these lines are, maybe there's no such thing as a line segment on a sphere. And Anonymous says, oh, if the line was taken off the curved
maybe
surface.
There's more than one.
Maybe there's more than one, right. A line on a given plane passing through 2 points on the same plane. So Kerdame in chat has got a definition which works in 3D space. If you're floating in space, not on a planet, but just in 3D space, find your 2 points, and then put in a 2D plane that goes through those 2 points, and then do all your geometry on that 2D plane. Which is fair enough. What did Ria say? Did I miss Ria's point? Ria says a straight line is not a curved line, multiple question marks. Okay. So let's make this work. If A and B are on the equator, I think Beth's going to be back in a second. Let's imagine that you're planning a trip from A to B, and both of those places are on the equator. I guess maybe I'm doing a sleight of hand here by saying what's a straight line and then defining a line segment. Possibly there's no definition that you'll accept of straight line on a sphere because, come on, everything's curved on the surface of a sphere. Possibly there's no definition you'll accept of a straight line, but maybe I can get away with line segments, if that's all right. There's probably some people in the chat who say, no, you can't have line segments either, because line segments are parts of lines and you don't write lines, but yeah. Hi, Beth. We're imagining that points A and B are... Hello. We're imagining that A and B are both on the equator, and we're trying to plan the kind of shortest path between those 2 points. I'm claiming that this is sort of an obvious case for what you should do if you want to do the shortest path between A and B. Yeah. Anonymous says a straight line might mean that the direction isn't changing. That's not quite what they say. They phrased it as a triple question mark sort of question, but maybe so. Yeah.
I see the vision.
Yeah, I get where they're coming from. Is my question too obvious? I think my question is too obvious, right? That we should, if you want to get from A to B, and both of those things are on the equator of the world, well, the shortest way to get from A to B is to stay on the equator. Maybe that's too obvious. Beth, you're more in touch with the people of chat than me. Was that the sort of thing where was that the sort of thing where it was too obvious
if you
and nobody wanted to say it?
Or... not being. Probably. No, you guys got this.
It's either the sort of thing that's too obvious and nobody wants to say it, or I'm making no sense and nobody wants to say it.
Everyone's confused.
It's one or the other, no midpoint. So like this would be stupid, right? Not this. Winding up and down into the two hemispheres. You should just stay on the equator. I feel like I interrupted you there, Beth. Sorry. Ooh.
No, I was just gonna say, if you go off of the equator, that's gonna take more time than just staying on it, right? Surely. So
yeah,
just stay on.
Yeah, good. Right. Wagon Wheel in chat. There's another biscuit. Wagon Wheel in chat says
that's a good biscuit.
You should go straight through the Earth. You should burrow from point A to point B via.
Ooh.
Wagon Wheel's got an idea in mind about what a straight line is, right? The shortest path between 2 points, which would be to get some sort of tunneling machinery and to go for it. So I guess maybe I need to add the restriction, right? That a line segment, the shortest path between 2 points that stays in the surface we're talking about. So if we're talking about a flat surface, then do your straight lines in the flat surface. If we're talking about the surface of a sphere, I want you to stay on the surface of a sphere. And I guess I agree that maybe all of this is going to seem stupid because the sphere lives in 3D, really? Like, the world feels quite two-dimensional and flat to us, but actually it lives in three-dimensional space. And distance in 3D is something you probably already know about, that you can use Pythagoras or something to find that distance. But I'm going to say, bear with me. What if you have to stay on the surface of the sphere? Good. Yes. Yeah, so I have a horrible opinion. Well, not opinion, but Ria's put something about lateral and lines of longitude and lines of latitude in chat, and Aaron's got something about having a constant vector, kind of constant vector. It's interesting, isn't it? Because if you go all the way around the equator, your vector of motion. Your vector of motion is changing as you go around, because it's a bit like you're orbiting around the Earth as you go around. So your vector for motion is different in different places, from the point of view of an observer. The vector approach is going to need some extra work, I think. Cool. I want to draw another sphere, and then I want to draw another sphere and say, if A and B are not on the equator, and I suppose this case looks harder if A and B are not gave it away. If A and B are not on the equator, but my plan is to rotate my head for this problem. If A and B, if you're getting between 2 points that are not on the equator, to rotate your head until it looks like they are on the equator. To rotator the equator and draw in rotator. Thank you, Beth. It's good to know I didn't get away with that. To turn my head sideways and draw in a kind of fictional equator at an angle. these have got names. Yeah, there you go. Okay. These have got names. These are called, in general, these are called. So I finished my sentence. Draw an equator. Small e. These are called great circles. I've seen that phrase in chat.
They're just really cool.
They are really cool. They're great in another sense as well. You can work out the etymology. Like they're great as in brilliant, but also great as in, I don't know, slightly more obscure etymology maybe. They're great as in big. They're really large. If you have like circles where you've sliced through an orange or something to get a nice circular cross section, then the biggest circle you can get comes from slicing right through the middle of the orange. And any angle is fine because it's a sphere. All oranges are perfect spheres, right? So you can slice through the orange at any angle, but you want to go right through the middle to get a great circle, the kind of biggest circle you can get. Wagon Wheel now wants to do teleportation between 2 points. So technology innovation. I was thinking about that. Actually.
That's not allowed.
It's not allowed, is it? Let me grab a bit of paper. Oh, there's a good bit of paper. Because the thing I was thinking about showing you is a kind of wormhole model. Oh, this is going to go badly. You do lots of flat geometry.
I like this.
Do you know what I'm going to do? Oh, I thought I just... Oh, okay. Beth's going to commentate while I... Beth's going to... Go on. Team effort. Beth's going to commentate while I demonstrate this.
Okay. So he's going to like pretend that paper is the universe. And he's going to like fold it because you can fold the universe. And then I think if he has a pen to hand, he's going to punch a hole through it.
Oh, okay. I wasn't.
No?
I will now.
That's the fun bit, though.
And I guess the point about shortest distance?
There we go.
Is something like, this is your universe. You can travel around using your flat geometry, where the flat geometry still actually works. Even if the paper is rolled up, you can still do your geometry staying on the paper, but a wormhole would be something that sort of connects together different points of your universe, providing some sort of shorter distance between those 2 points. So I suppose the restriction I would like to use is no wormholes, no connecting points together, no stabbing it with a pen. If we're doing motion on a surface, I would like you to stay on the surface without teleporting or tunneling or wormhole between 2 points of the surface. I think I should let Beth direct more of the maths club. That was way more dramatic than what I had planned.
I know. You got...
I want to watch that back afterwards. I think it's the most violent thing I've done on the maths club. Right. Does this mean... so there's a question, does this mean that a wormhole... And then I'm really not going to comment on wormholes. They say, is it a spherical hole? And I should just not comment, I think. Good. Right. So... in particular, this tells you how to find the shortest route between 2 points on a sphere, provided that you can just travel in what feels like a straight line to you while you're doing it. You're not changing directions while you're doing it, which is actually quite impractical on the surface of the world because there's all countries in the way and stuff, unless you're in a plane. So I have some flight maps. I went and checked some flights earlier today, and I picked.
Where are we going?
I picked this one. We're going to Chicago. I think we took off.
Oh, nice.
Somewhere in, I want to say, Saudi Arabia, all the way over here. So there's a bit of wobbly.
How did we get to Saudi Arabia?
Down here, I think the purple line, but it's this bit that I'm interested in, where the plane does this, which on the map maybe looks totally crazy. Is the pilot stupid? Why did they not simply go through here? Answer, they are terrified of the Bermuda Triangle. No, not really. Answer, this is actually a shorter distance. Even though it looks like loads of distance on the map's kind of lying to you. And on the spherical world, this is the shortest route. I guess the question is that a straight line in purple at the top? Not my planned route, but is this a straight line? Kind of, a little bit. It's the shortest distance between those points in Norway and Northern America. So it kind of works a bit like a straight line. I think it's time for the sort of horrible realization, though. We had previously on the live stream, we had lines of longitude and lines of latitude. Maybe this is not. Maybe I shouldn't sell this as horrible. It's not that bad. But we had lines of longitude, which go round like this through the North Pole and through the South Pole. See if I can draw these. Oh, it's not my greatest drawing. Chat, if you've seen previous episodes, what was my greatest drawing? Actually, maybe don't answer that. Unlikely to go well.
You drew a sheep that was quite good.
I drew what, sorry?
A sheep.
Oh, right. Oh, yeah. Okay, earlier this episode. Right, okay, yeah, that's bad. I don't answer that question. Okay, right. I walked right into that. I was so excited that you'd remembered a sheep.
Oh, you're welcome.
Thanks, Beth. The snail from last year is the vote in chat. Good. So lines of longitude. Lines of longitude are great circles. I should go back to typing, shouldn't I? Brief experiment with typing. So this is a bit of a weird realization that if you need to fly from the North Pole to the South Pole, then there are lots of shortest routes from the North Pole to the South Pole. Maybe that's not so weird. I think you know that if you're running around a circle and you need to get from A to B, then you could go that way round or you could go the other way round. Those are sort of equally good. But there are loads of these great circles that go through the North Pole and the South Pole. Maybe chat's seeing where this is going. There are also lines of latitude. And lines of latitude are not great circles. Not great circles. They're only okay circles, except the equator. Before chat gets to me, before chat gets there, except the equator is. Right. Okay. So sort of. This says flying your plane due south is an okay idea. Flying your plane due north is an okay idea. But flying your plane due east or due west is unlikely to be a good idea if you're doing it for a long time. And it means that in our example with the bear at the start, nobody's going to let me have this, are they? In the example with the bear at the start, where you run south, then east, then north, I think that one is a straight line. I think that one's a straight line, but I think the middle one is not a straight line. I don't think chat's going to let me get away with that. I think that two of those are straight lines and one of those is not a straight line. Oh, let's find out if chat's going to at me. Because you're not running along a great circle.
But it's perpendicular to two straight lines.
It is perpendicular to two straight lines, but you can do examples on flat space that are weird, right? Like, so if you had two straight lines perpendicular to two straight lines, but it's not a straight line, would be something like this, where I have my two straight lines and I have this weird not a straight line. It's part of a circle or something. And it's perpendicular but not a straight line. And I think that's kind of what's going on here. That we've got two straight lines with some angle, and we've got a not a straight line. So for me, straight line, if it means anything, it means a shortest path between 2 points. And possibly because you were stressed about the bear, but when you did that bit of running east, I mean, not only was that not taking you away from the bear, but also it wasn't even the fastest way of getting from here to there. It's close. It's close. You're near the North Pole, so you can get away with a lot. It's a very small triangle, so it's probably fine. Right. That's a triangle with, well, am I going to call this a triangle? I'm not really sure I can call this a triangle because it doesn't have 3 straight sides. It doesn't have 3 line segments for its edges. So for me, a triangle has 3 line segments. Let's write that down. It looks stupid, but let's go for it. A triangle is made of 3 corners. Welcome back to the Oxford Online Maths Club. A triangle has 3 corners.
Advanced spell.
I shouldn't say the, and line segments connecting. Let's go for 3. I'll be bold. I'll say that a triangle has got 3 sides as well. So that definition kind of works in Euclidean geometry on the plane. I'm saying Euclidean geometry like Euclid, ancient Greek person. Yes. So let's get some examples of triangles. I guess one of them is, e.g., the Bermuda Triangle. Maybe. So if you pick 3 corners, I can't remember where people put the corners of the Bermuda Triangle. It's probably one of them's Bermuda, one of them's maybe Panama. No? Do you want to guess the third one? I think you could put it anywhere. It's just the Bermuda Triangle. Where should we put these? Maybe Florida. I'm going to put Panama as my third corner. And direct flights between them. So there's ways to connect those 3 points. There's ways to connect those 3 points with not straight lines. If you want to do a little wiggle to include some extra shipwrecks or something, then be my guest. I mean, it's just the Bermuda Triangle, right? You could do a little wiggle. But if you want, for me, a spherical triangle would be made of line segments. And just like in the plane, if you've got 3 points, it's not just freestyle for the edges. I want you to do line segments. On the sphere, if we're talking about a spherical triangle, really for the Bermuda Triangle, I would like direct flights, or these kind of lines that are part of a great circle between those 3 points. Chat says Puerto Rico instead of Panama. I'm going to stick with it.
Chat is very knowledgeable.
Chat's good, aren't they? Yeah. So does the Bermuda Triangle have 3 straight sides? Well, that kind of depends who you ask. Also, where are the corners? Depends who you ask. But you can make a spherical triangle like this. Okay, so question for chat to demonstrate that these spherical triangles are a little bit weird. Can you find a spherical triangle with 2 right angles? We got quite close before with the bear example, except that bit in the middle is not really a straight, not really a line segment for me. It's a sort of curved bit of running that you did. I feel like that's got to confuse chat. That's exactly the sort of thing that I do that confuses chat, I think, where I say, no, these curved lines are straight, and then I point at one and say, that curved line is a curved line. Like, what? My definition, just as a reminder, is I would like the line segments to be parts of great circles. Great circles are the biggest circles that you can see when you slice a sphere. The slice goes through the middle of the sphere and you get a great circle, the kind of biggest possible circles. Parts of that form line segments between A and B. Oh, sorry, a spherical triangle is a triangle on a sphere. Let me rephrase that. Can you find a triangle on a sphere that has, okay, that's a bit better. So on the plane, no, you can't have 2 right angles. On a sphere, yeah, what's an angle? Okay, I thought maybe I could get away with angles. I'm not getting away with angles. Let's talk about angles. I'll talk about angles, and maybe chat can think about where to find right angles or any example of a triangle. Okay. Actually, let's get Beth involved again. Hi, Beth.
Hi.
I'm trying to describe. Yeah, sorry. I'm trying to describe I don't quite know what I'm going to ask you to do. I'm trying to describe this triangle where I've tried to draw them not conventional straight lines. I've tried to draw them as if they're part of, just to be clear, part of a great circle that goes all the way around the world, and that slice would include the centre, great circle. Because that's a really short route from A to B. Chat's asking about the angles, and for me the angle is what you get if you zoom in really close. So there is some angle here. The angle is what you get if you zoom in really close. Hi Beth, I'm trying to explain angles where I think my definition is something like, for the angle, just zoom in really close. Here's my magnifying glass. Zoom in really close and have a look at what the angle is there nearby. I think angles do the thing that you want. Right, Joe's got a suggestion of a triangle. Let's draw that one. I think Al's got one. So Joe wants to put base points are on a line of latitude and the top point at north or south pole. I'm going to make you come down to the equator, I think. But yeah, same. That's the idea I've got in mind, I think. If you have one corner at the North Pole, one corner on the equator. I should have looked up a list of countries that are on the equator, because I'd quite like 2 countries that are on the equator. Wait, let me think. Equatorial Guinea is on the equator, and something surprising like Brazil or something. Maybe not Brazil. Yeah, oh, there you go. Anonymous is in. North Pole to the equator, and then due east, and then back up again. So Anonymous person's remembered that I want great circles, and lines of latitude are not normally great. Actually, most of them are quite small circles, but the equator is a great circle because it's a really big circle. Good. Okay, I think that this triangle has got 2 right angles because you go all the way down to the equator, and then the shortest distance from A to B along the equator is to just go around the equator. And then going north again is to get all the way back up to the North Pole. Effectively, what I'm saying, I think, for this example, is something like, if you take the bear problem, but you replace 1 mile with 10,000 kilometres. Every time. 10,000 kilometres, 10,000 kilometres, 10,000 kilometres each time. If you do that, then you'll make it down to the equator. And then I think all 3 sides are parts of great circles. This one, because you're running along a line of latitude. Sorry, a line of longitude. I've got to get those right. Line of longitude, that's a part of a great circle. And then the equator is a great circle. And then up this line of longitude is also a part of a great circle. Yeah, this is giving one person a headache. Cool. So that's pretty weird. For people living on a sphere, it kind of really is a triangle. It's 3 points, and those are the shortest lines you can draw between those 3 points on the surface of a sphere. But the angles are too large for planar geometry, too large for Euclidean geometry. I'm getting some interesting Zoom error messages. Hi Beth, can you hear me at the moment?
I can, yes.
Yes. Chat's quite upset about this triangle.
Oh, as they should be.
Right. I think they're upset because it's got 2 right angles, and I think some of them are probably upset because it doesn't really look like it's got straight sides. So.
But we've told what a straight line is, so you can't even argue with that.
I suppose, yeah. I think they are arguing with it. I think they would say they can. But, if you want to do flat geometry, then you don't get this effect, right? Because the triangles always have angles that add up to 180 degrees. But since we live on a sphere, maybe we should look at the triangles that you get just in our everyday experience of moving around on a sphere. And those triangles are weird. Those triangles do stuff like this. Yeah, Joe's right. These triangles can have 3 right angles. I suppose you can probably guess
That's just too many.
You can probably guess where we're going to put the 3rd right angle. We've got 2 already, and the triangle has this other thing at the top where we could fit another right angle up there. If these are sort of 90 degrees apart around the equator, perhaps. That one's got 3. You can actually have up to 5 right angles for a no, I'm just joking. You can only have 3. They've only got 3 corners. I couldn't even hold that joke for a second. I'm so sorry. You can have 3 right angles. Yes, but not more than 3 because you only got 3 corners. Wow, no, I feel really bad doing that intentionally. Good. I want you to notice that this triangle we're considering is really big. I'm going to label it. It is a really big triangle. In terms of the sphere, let's do it as a fraction of the surface of the sphere. So this one, as a fraction of the surface of the sphere, how much of the sphere are we talking about now? So this is quite a large camping activity now, I suppose, but as a fraction of the surface of the sphere. Anonymous has a great question. If the top angle was almost 180 degrees, would that still be considered a triangle? Yes. Because it meets by definition, right? It's got 3 corners. One of them still at the North Pole. A is still where it is. B has gone over there somewhere. Still got 3 corners. And the sides that you're thinking about are still parts of great circles. They're still the shortest distance between those corners on the sphere. If you're stuck on the surface of a sphere like we are, then the triangle that goes from A to the North Pole to B that's almost opposite A, that triangle includes quite a lot of the world. Could you have a triangle where every angle is nearing 180 degrees? Now we're talking. I will let you try to work out how to achieve such an enormous triangle. I asked a question and chat has answered the question. Beth, do you want to answer the question as well? What fraction of the sphere are we talking about here? With the one on the screen.
Oh, like an 8?
It is an 8. Good.
Yeah. I was bringing in my Terry's chocolate orange knowledge.
Right. You can never just have 1/8 of a Terry's chocolate orange though. Not sponsored.
That's true.
If they're watching, then for the price of a Terry's chocolate orange, I reckon I would. If they send me one a week, then. Right. Okay. I do actually want to talk about segments of a circle. It would be the segments of a sphere. It would be so convenient right now. So observation, and I think I've got just about enough time to do the proof of the facts that I want to do. But observation for now. This triangle's weird. It's got lots of right angles, but it's also huge. Those facts go together. Very small triangles on a sphere behave like everyday triangles because a very small triangle on the sphere, well, can't even tell you're on a sphere if you have a small enough triangle. But a very large triangle, you start to get this effect where the angles might not be what you're expecting. Okay, we can make a 2D object and a 3D plane out of 2D straight lines. We can make a 2D object in a 4D plane out of 1D straight lines. I don't totally know how to make a 2D object in a 3D plane out of 2 straight lines. Oh, maybe I do. Is that referring to this kind of lunette thing? I'm going to draw one in a second. Going like a 2D object in a 4D plane of 1 straight line. I think the answer is no. But... Oh, so where's the answer? 1/8. Beth, do you want to say how you got to 1/8? Really putting you on the spot. Sorry. So this is 1/8 of the 1/8 of the sphere.
So.
And you said Terry's chocolate orange knowledge, and I got distracted.
Yeah, really, that is the reasoning. Have you ever seen Terry's chocolate orange?
Again, they're not sponsoring us. So
I wish they would.
I suppose one way to approach this is to think, let's think about the upper hemisphere and the lower hemisphere separately. This triangle lives in the upper hemisphere, so let's forget about the lower hemisphere for now. What I could do, because of a right angle is 1/4 of the angle at a point, I could draw in some more of these. So I can imagine running this great circle around here to the equator and this one left out to the equator. And then one of my worst drawings ever, but it's sort of, the top hemisphere has been chopped in twice. So we have 1/4 of that top hemisphere. It's been sliced like on the X plane and on the Y plane. To get this right angle at the top, chop. So it's sort of been chopped 3 times overall, once to get the upper hemisphere, and then vertically at a 90-degree angle. So that 90-degree angle gives you 1/4 of the top hemisphere. Good. People in chat think 1/8 as well. Draw a line from north to south and another one next to it. Nice. Okay. I don't need to do that much. It's just obviously 1/8. Okay. Yeah. Fine. Okay. Right. Let's see if I can over-explain something else. Chat's gone. I love anonymous chat. I'm never switching it off anonymous. The ability to be anonymous and say what you're actually thinking is fantastic. I love it. They're also now trying to divide by 0, which is the one thing that we've banned.
Oh, come on, guys.
Yeah, good. Okay, so spherical triangle. I want to prove something that relates together the area of the triangle with the angles. In order to do that, I've got a little spherical triangle here where the edges are red, yellow and blue, and I've drawn in the great circles that make up those edges. Maybe this was quite nice because the triangle looks like maybe it's got straight sides, but those are parts of these big circles. I'm not really sure if you can see through. I don't know how this is coming through over Zoom, but can you see the kind of shadowy bit around the back? I might have to draw it in. Might have lost Beth again.
I can see a couple.
You can see a couple, right? Okay, I'll draw a bit.
Don't worry. The orange one's a bit faint, but the red one.
Okay. The red one's good, right? We'll work with red and blue if we can then. Good. Yeah, we've got this, right? It kind of looks a little bit, if you can see all 3 of the hoops, it looks a little bit like a atom emoji, the one with the hoops going around, because it's sort of things going around a central point. There's this reason it looks like, that's what people used to think atoms looked like. We know what atoms look like now because we did a really, really complicated live stream on it. Okay, here's what I want to, it was a whole thing. Here's the area that I want you to think about. It's the area that, let's go this way around. So between red and blue, I'm going to shade part of the sphere, including this bit around the back, between this red line, which goes out and then comes back again around the back to here, and this blue line.
That's an excellent drawing, James. Well done.
Thanks, Beth. If people missed a previous live stream where Beth was on the first time, they might not remember that Beth is one of my students, and I get paid to get this kind of feedback from Beth.
Yeah, you're welcome.
You mentioned New College, but well done. I thought you mentioned New College very subtly, which was very good. We're at New College. It's one of the colleges. Right, okay, what have we got?
It's the best college.
We've got chemistry again, here we are. Okay, so this bit of the sphere, it's got part of the surface area of the sphere, and I'm doing this with my hands because I'm imagining opening it up around the back point here and this point here like a pivot, to open it up like this. Like it's a big sort of smile, or maybe like Pac-Man opening and shutting its mouth, like whack whack.
It's Pac-Man.
It's Pac-Man.
It's 3D Pac-Man.
3D Pac-Man. So I'd like to know this kind of motorcycle visor bit, or the mouth of Pac-Man. This is quite hard, I suppose, but there's a relationship between the angle here. Maybe we'll just play along like this. There's a relationship between this angle, which I'll call alpha, because I like to use Greek letters for angles. There's a relationship between that angle and how much area you get. I guess the larger alpha is the more area you get. Beth, you're good at formulas. Can you see what sort of formula I might get for that area?
Yeah.
Ah.
Not on the spot. Sorry, James.
That's all right.
Can chat help me?
Chat can maybe help, right?
So help me out.
If alpha is 0, you get none of the surface area. And as alpha increases, you just get more and more surface. Until, I guess, if alpha were like 360 degrees or something, you would now get all of the surface. I don't know, maybe chat would prefer to think of if alpha is about 180 degrees, you get half of the surface. So there's some relationship where you have none of the surface, and as you open up that angle, you get more and more of the surface of the sphere. I will let chat have a go. Yeah, Wagon Wheel's having a go at doing a formula for how much you get as you go round. Yeah. I haven't told you the radius of the sphere. Oops. So they're going for either. Yeah. I was sort of hoping chat knows the surface area of a sphere. I didn't check that. 4 pi r squared, chat. 4 pi r squared for the surface area of a sphere. Yeah. Okay. Yeah, so whatever it is for a sphere times alpha divided by 360 degrees. Love it. Okay. 4 pi r squared times alpha divided by 360 degrees. Good. Okay, that's the purple area. Got 10 minutes. Okay. I need to do a green area and an orange area in kind of the same way. I'm going to try my best, I suppose. What have I got? I want the orange area to come out this way. So between red and yellow. The yellow is already quite orange, but we'll do our best. So I'm going to shade like this bit of the sphere, and then around the back, like that, around to this point. So this is part of the sphere, and all of the triangle again. And kind of orange. I'm making a kind of beach ball pattern, I suppose. And hopefully if I give that angle a name as well, to call it beta or something. Because it's the second one here. Joe wants to know why New College is the best college. Beth, do you want to say anything nice about New College while I'm doing?
What? Because James is here. Also, it's really pretty.
Thanks, Beth. Checks in the post.
And we have a cat.
We do have a cat.
You're welcome.
We also have parts of the old college walls, which is a historical feature from when Oxford had city walls around. So we've got some old masonry if you're into architecture. I don't do a lot of advertising in New College. Maybe I should do more.
If you're into history.
If you're into history.
Yeah, New College.
There we go. And Anonymous is looking for information about summer schools. For summer schools this year, we've already done some work to find people for Unique, which is our main summer school this year. Right at this point. The Murray Edwards one is still taking people signing up for that one. So there's more summer schools out there. If you're not in year 12, if you're in year 11 or equivalent in other parts of the UK, then maybe Unique next year. Okay, I've written down similar things for a green area and an orange area using the other ones, using the other angles. I've completely obliterated where it says alpha. Like the angles are called alpha, beta, and gamma. Okay. I love this proof so much. I think I can do it now. The bits that I haven't shaded are round the back. There's a kind of shadow copy of this triangle, The word is antipodean for points that are on the opposite side of the world, like how we're on the opposite side from New Zealand, and parts of the US are on opposite sides, opposite from parts of the South Pacific or something. Antipodean on the other side of on the other side of the world. Long word. There's a triangle on the other side. It's got quite hard to see, and there are some regions. The big one on the other side between red and yellow, between blue and red, and between blue and yellow coming around. But those are just the same. They're just opposite. Each time I draw one of these regions, there's also a region around the other side of the same area. So there's some unshaded grey stuff, but the unshaded grey stuff is the same area overall as there's the colourful, coloured in bits of this beach ball picture. I could go and give them all another colour, or I could colour around all of those bits and convince you there's a green bit at the top and an anti-green bit around the bottom, but I'd have to decide what colour anti-green is, and I think I'm just gonna go for that. But if you add up all of these if you add up all these colourful bits, you must get half the area of the sphere overall. Add for half the surface area. Oh, my handwriting has got worse. There we go, I'll slow down. But wait, there's some double counting. If I just add these numbers together, there's some double counting. Maybe you can see why. Yes, someone in chat says, is the sum not just half the total area? And they put like 5 question marks on it, which is code for yes. Yes, it is. adding those things in total, the colourful bit is half of the sphere, but there's double counting, right? Hopefully you can see where the double counting is happening. I'm going to put Beth on the spot because I'm running out of time. Chat's definitely typing it, but where's the double counting when I add up these?
It's looking like where you've coloured the same place multiple times.
Yeah,
the triangle.
The triangle. Yeah. So if I just add these things up, then I'll triple count the triangle because it's in all of these. So the true statement that I can write down is that I should add them, but this would triple count the triangle. So I'm going to subtract twice the area of the triangle, which I suppose I don't know, and maybe that's the thing that I'm trying to work out. So minus 2 times, and then I'll just write area of triangle, like this. 2 times area of triangle. Okay, so if I do that with the double, allowing for this double counting, that adding all of these is the colourful area, but that's triple counted the triangle, so I should subtract 2 times the area of the triangle. I only want to single count that bit. I should get half the area overall of the surface area of the sphere. Yeah, that little triangle. Yeah, that little triangle's been triple counted, so we should subtract 2. This formula is really good. It simplifies quite a lot. How do I want to simplify this? Probably I want to go something like pi r squared. Maybe I'll bring out the 4. Yeah, I'll bring out the 4 as well, I think. No.
It looks so pretty.
It's so good. There's so many pi's everywhere, right? I normally do this in radians, so I'm going to think really hard to make sure I get this right.
I was going to say, if only we were in radians.
If only we were using radians.
Chat, radians or degrees?
I really want this to be 2 pi so that it cancels. Chat can let us know. Yeah. It is going to be something like alpha, beta, gamma, and they're not going to sum to the thing that you want them to. I think I need a 2 out here. Maybe a 2? No, okay, so we're going to pull out the 4 pi r squared, and I'm just going to go like this. Alpha plus beta plus gamma. Here's the fact. I regret that 360. 4 pi r squared minus, and then 1/2 is twice the area of the triangle. just moved a term onto the left-hand side at the end of the day there. All that thinking, and then all I've done is move the thing on the left-hand side. So this formula is amazing. This tells you that if your triangle is very small, if you have a small triangle on the sphere, then this stuff is approximately 0. And a result of that would be that the sum of the angles in your triangle is about half of 360 degrees. It would be about 180 degrees for a very small triangle. But for a very large triangle, it's still true, and it tells you the area. It tells you the sum of the angles in a larger spherical triangle. I think this is the main way that spherical geometry is a bit weird. It's weird that given the angles of a triangle, you can work out its area. And given its area, you can work out the sum of its angles. Those things are not related to each other in planar geometry, where all triangles have the same sum of the angles, and you can vary the area and it won't affect the sum of the angles. For triangles on the sphere, which is where we live, the larger ones have a larger sum of the angles in a predictable way. There's a nice formula for it that comes from just thinking carefully about areas on the surface of the sphere. I think I got there. Beth, do you think I got there?
So cool.
That's good enough, I think. So Anonymous in chat says, do alpha, beta, and gamma sum to 180 a moment ago? And the answer is not quite. Only up to
No.
the area. Yeah. Good. Right. Okay. I think I'm going to call it there for some spherical geometry. I'll put some stuff in the further reading if you want to find out more about this branch of mathematics. How did I get to the half? The two area of right-hand triangle has gone onto the right-hand side, and the 2 pi r squared has gone onto the left-hand side. That's why it's 1/2, because it's secretly 2 pi r squared. But they've just swapped sides. I wanted to get rid of this minus sign, and I wanted to bring all of the pi's and r squareds together.
He's done a lot of complicated algebra very quickly.
I actually think I did it quite slowly though, because I was trying to do about 3 things and I was certain I could do all of them in my head, which was probably a mistake. I should have written out 3 lines and done all of them. Oh well, we'll leave that as a puzzle for people to think about. How did I shuffle around all those terms? Right, good. Okay. Thank you very much, Beth, for appearing on the live stream again to join in with spherical triangles. Thank you, Rowan, who's been moderating chat and making sure that nobody divides.
Thank you, Rowan.
Thank you, Rowan. We will see you in 167 hours for another episode of the Oxford Online Maths Club. But until then, have a nice evening, have a nice weekend, and it's goodbye from me. And it's goodbye from Beth as well.
It's goodbye from me.
We didn't rehearse that. I'm so sorry. I thought of it just now as a great way to wrap up. Didn't set you up at all.
It's like University Challenge.
Just like University Challenge, yeah. Everything about this is just like University Challenge. Right, we're still live. I should probably do something about that. See you next week, everyone. Further reading notes, if you want to find them, they are on the Maths Club website. I usually write them on Friday. Please have a look at the Maths Club website where you can see further reading for all of the episodes we've had this year, including Beth's episode from earlier this year about fundamental theorems of calculus.
They're really good.
We're going to try wrapping up again. We will see you next week. Bye, everyone.
Bye.